This video is going to look at the reactions associated with benzene. Before we talk about reactions, let's think a little bit about what happens when different substituents are on the benzene ring. If we think about what's happening if we have a substituent that is more electronegative than carbon, it's going to withdraw electrons, and what that means is it's going to be able to stabilize having a negative charge on an oxygen. So for example, you could draw resonance that allows you to extend the negative charge from the oxygen onto your electronegative atom. That means there's less electron density on the oxygen, making it better. You can also withdraw electrons inductively. So here we have a more electronegative atom, but we aren't able to extend resonance into it. So we're going to say that if it's something that's more electronegative than hydrogen, it's going to withdraw those electrons from benzene more than a hydrogen will. An alkyl group is one of the exceptions in that it will donate electrons through the process of hyperconjugation. Having an electron donating group allows you to draw resonance structures using the lone pair to extend into the ring. You should be able to draw the resonance structures for this picture with the arrows, as well as the several others for this structure. The key to identifying an electron donating group is by looking to see if the atom has a lone pair, that is the atom attached to the ring. This is important because these groups will be orthopara directors during the reactions we'll talk about later. You also have electron withdrawal groups. Again, you should be able to draw resonance structures for these as well. The key to identifying whether a group's an electron withdrawing group will be whether or not it has a double bond or triple bond connecting the atom on the ring. These are important because these will be meta-directors. Now there are a couple exceptions to these rules, but really you can use lone pairs or double or triple bonds to identify these two groups. What this means for pKa's and acidity for these compounds is that if you have an electron donating group, it's going to decrease acidity. If you have electron withdrawing groups, they're going to increase acidity. So I show you this picture, not that you need to memorize pKa's, but to be able to associate whether or not it would increase or decrease the acidity of a compound. These are carboxylic acids. The bottom groups are phenols, but you still see the same trend having those groups make those effects. The main reaction for this chapter is known as electrophilic aromatic substitution, and as we talked in the last video, the advantage of aromaticity is that the compound is now containing increased stability, meaning the reactions we talked about with traditional alkenes are not going to work. You'll see a lot of similarities, but we're going to have a really hard time making an electrophile causing those double bonds in benzene to become nucleophilic, but you should see some similarities in how we draw the mechanism. The end result of this product, electrophilic, meaning we're going to be generating an electrophile, aromatic because our compound's going to be an aromatic ring, substitution because our electrophile and hydrogen are trading places. So all three of these words you should understand. These are going to react with electrophiles very similar to alkenes. It's just the type of electrophiles we're making are going to be very different. Notice your arrow here, your double bonds acting as the nucleophile, picking up your electrophile. This creates a carbocation at the other position. This is going to be exactly like an alkene. So if we look back, this is what we drew for an alkene mechanism. You can see it grabbing its electrophile, carbocations at the other position, and your nucleophile would come in. This last part's going to be a little different for electrophilic aromatic substitution. So if we think about the first step, it's going to be very similar to what we drew with alkenes. The next step, however, is right now we do not have an aromatic compound. We have an sp3 carbon at the position where our new electrophile was added. So in order to retain aromaticity, a base is going to come, pull off this hydrogen, and you actually have an elimination reaction. This allows us to trade a hydrogen for our electrophile, and at the end, we gain our aromaticity back. So that's why this reaction will be much faster. If we think about the two possibilities after we've added our electrophile, looking at route A, if we have our nucleophile come in and add at the position where the carbocation is, then we are not going to be aromatic anymore. So it's very advantageous for our Z minus here to take the hydrogen and acting as a base, allowing us to gain our aromaticity back. And the only thing that has changed from what we started with is instead of having 6 hydrogens, we now have 5. The key for these reactions are generating your electrophile, and we'll talk about some similarities. There are going to be 5 main ways a benzene can undergo reactions. The first one we're going to talk about is halogenation. We can add either bromines or chlorines. The first part is going to be having the lone pair of the bromines add into the empty p orbital of our iron 3 bromide. This is going to create a positively charged bromine at this position. This lone pair donation is actually going to weaken your Br or Cl bond, allowing that bromine to push its electrons on to the bromine that's going to stay attached to the iron, giving you a positively charged bromine, a very strong electrophile that will attract benzene. Your arrows for nitration are going to be very similar to the next mechanism. This is going to involve your nitric acid using the lone pairs on one of the oxygens to go out and grab a hydrogen. So we're essentially using sulfuric acid to protonate nitric acid. You should see here that if once that oxygen picks up that H, it's actually going to make water, a great leaving group. At this point, those electrons are going to be pushed onto the oxygen, and you now have created again your electrophile, the nitronium ion. That will be enough to attract the benzene's nucleophile. The arrows for sulfonation are the exact same. Notice again your O is going to go out and grab your hydrogen, push your electrons onto the other piece of the sulfuric acid. Water again is going to leave as a leaving group and will create the sulfonium ion, which will then add to your benzene. So looking at these 2 mechanisms, you can see that yes, they are 2 different ones. You're getting 2 products at the end, but the arrows for how you're getting there are basically identical. The last 2 mechanisms are going to be the main way we make new carbon-carbon bonds on a benzene ring. This first one is called acylation. You may have seen this functional group before. Notice here this is a carbonyl group with the carbonyl carbon being attached to a chlorine. This mechanism is going to look a lot like the bromine mechanism we started out with. The lone pairs on the chlorine are going to go out into the empty p orbital of the aluminum. That's going to make this carbon-chlorine bond a little bit easier to break, making our electrophile. This is known as the acylium ion, in which the carbon of our carbonyl group is now going to be attached to the benzene ring. If you don't want a carbonyl, you can also just use a traditional alkyl halide, where our chlorine arrows are the exact same, pushing your electrons onto the chlorine, and now you can generate your carbocation, which is a strong enough electrophile for benzene. Again, looking at these 2 mechanisms, you can see there are a lot of similarities, so you really don't see a lot of complexity between the 2.